Hey, Mike.
Hey, Advent of Code is over. We should talk about that.
Yeah, that's probably a good idea. Let's do it.
All right. Welcome to Hacking. Oh, blah. Welcome. Welcome to Hacking the Grepson, a podcast about programming and development. And we are in the middle of December, so of course that means Advent of Code. This year, normally we'd be in the middle, probably in a problem that I would be laughing at when I read the description and maybe trying later. But instead, we're actually done with Advent of Code because, as we said in our previous episode,
Woohoo!
There are only 12 days of Advent of Code this year.
And in retrospect, I think I liked that.
I also like that. I wonder if anybody wrote a version of the 12 Days of Christmas, but the 12 Days of Advent of Code yet. I feel like that's a thing someone would do.
Get on that, Mike.
Yeah, I'll think about it. So, we're done with Advent of Code, but we still need to cover the back half, which is day 7 to 12. We attempted day 7 on our last episode and got some of the way, but we didn't finish it, so we're going to go back to that, but then we got to finish 8, 9, 10, 11, and 12. Any like initial thoughts, though, just about this year and the problems? I mean, did you get through them all, Matt? Because I did not get through them all.
I didn't do day 12. Okay. I did not get through both parts of all days either.
Okay.
I think if I could find my calendar, there it is. I got through all the days, both parts, days 1 through 9. Did not get the second part on day 10, and as I will discuss, accidentally cheated for day 11 and got the answer. And then I have an idea for how to do day 12, but I don't have time. It's really what it boils down to. I thought, like, if you were to take the difficulty curve and map it across the normal 24 days that we do in Advent of Code, felt about right. I was hoping it would stick more towards the first 12 days of Advent of Code instead of delving in. But I really only felt like the last few were like particularly in trying to deal with.
Yeah, I agree. I don't think it went as hard as most past years in terms of difficulty, but it definitely did the usual ramping up near the end, which is why. So I'm looking at leaderboards, and I was actually in 2 leaderboards this year because I got my 2 developer coworkers to do Advent of Code this year, and so one of them started their own leaderboard. So there's the 3 of us on that one, and then there's you and me and Richard and a few other people on the normal one that we have. And interestingly enough, Richard, and I know why, because I think he went on a trip and was not able to work on Advent of Code. But
I'm number 1.
Yeah, he dropped. Matt's number 1, and I'm number 2. And some other person that I don't know, and I'm not going to say his name, is on there. But Richard is like number 4, and he hasn't even finished day 7 all the way. So it's weird to see that, because normally Richard's at the top with a full, assortment of yellow stars.
I'll take my top. Hey, you did part 1 of 12. Cool. That means it must.
I did, and
must be more doable than I thought it was.
Yeah, we'll talk about 12. But looking at my other leaderboard with my coworkers, we're basically almost tied, except they both. One of them got part 2 of 9, but then none of us got 10 or 11, and then I got the first part of 12. So we all kind of like petered out at the same time. Yeah. I don't know. Just thought it was interesting.
Looking at the stats, it looks like day 10 was slightly harder than day 11, I think, because there are more gray stars on day 10 for under their stats page than for day 11. Like, more people got a gold star, and that jives with what I saw, because I was very close to getting part 2 day 11 on my own, and just we'll discuss it when we get there. Okay. I think the curve looks about normal, maybe a little bit less steep, less drop off than usual. On my 2 leaderboards, I'm number 1 on ours, and then on the work one, some people passed me. I'm number 11 out of the people who actually did it this year out of 34. So that's not bad. Everybody above me has either the exact same star setup as me or every single one done.
I think, unlike a year where there's 25 days. I could, if I spent some more time on day 10 and 11. I mean, I spent time on all of them, which is unlike any other year. Like most years with 25, there are just days that like I just read and I'm like, nah, not even going to try that. And I never go back to it. But this year I did make attempts on every single one of them. And we'll talk about, the troubles that I got into. So it was just nice. It was nice to actually have like some attempt at every single day. And I think 12 is a good number. And it's nice that it's done and it's wrapped up, and then you still have the second half of the month to, do Christmas and Hanukkah and whatever holidays you do during the winter. So yeah, I'm perfectly okay if this is how it goes for the the rest of time.
I also think that work is probably happy about this because I'm sure that there's plenty of people, not my work in particular, but like software engineering houses in general are probably happy about this because I'm sure people work on these things during the day. I know I do periodically. Like I'm like, it's bugging me. I got to go look.
I think this is personal development. Like nothing in Advent of Code like necessarily maps one-to-one to anything I do at work, but just problem solving, logic, thinking about, how something works, an algorithm, like that's just useful for any developer, programmer in general. It's just, it's a good way to like, I'm always like, there's a mood and a vibe when Advent of Code is going on. I mean, for me, it's as much joy as it is frustration, but like, there's just like a cool, like, oh yeah, it's Advent of Code. That means I'm going to start, clearing out the cobwebs in my brain about algorithms again. And let's see if I can do a little better than last year or so.
I find that my skills in doing things like dynamic programming in particular have grown significantly, possibly exponentially.
Wow.
Which means I have to use dynamic programming. Since starting Advent of Code a few years back, like since starting doing it regularly, like this year I noticed when I would go to approach a problem, my brain went there first rather than, okay, I'm stuck here. I guess I should memoize or whatever. So, should we dive into it?
Yeah. Let's do it. Yeah. All right. So, we're going to head back to day 7, which, as I mentioned, we did try in our last episode and did not finish, but let's just quickly go over it again. It's called Laboratories. Essentially, you have a 2D grid where you, let's see, this is a teleporter lab, and you are looking at a diagram of the tachyon manifold, which in layman's terms basically means there's a bunch of dots, except at the very top middle there's an S, and that's where your tachyon beam is going to start from, and it's going to shoot downwards towards the bottom, and when it gets to the bottom, it's done. But if it hits a tachyon, or a splitter, which they use the caret symbol to denote, then the beam stops and it splits to either side and then continues down. And so part 1 they wanted us to do is basically ask us how many times does the beam split if it starts in the middle and goes down and hits a splitter. And I remember initially we were like, oh, the sample data was 20. It says it splits a total of 21 times. And we're like, wait, why doesn't that just equal the number of splitters? Until we better looked at the graph and noticed that some beams are, there's one splitter that doesn't get hit because the beam just keeps going down and never hits it. And I think soon after we finished that episode, you got it, and then soon after you got it, I got it. Yeah. And for me, I think the hard part was basically just, something that's recurring for me this year because I was using Lua is just parsing and figuring out the slight idiosyncrasies of Lua in how it handles data, because once again, Lua doesn't have arrays. It has tables, which are essentially associative arrays. And so that means that there's 2 different ways to add things to an array in Lua. You can insert them. So you can do like table.insert, the name of the table, the value. And what that does is it just numerically inserts them. So if you do that once, now you have table element 1 equals the thing you put. If you do it again, you have 2, 3, 4, 5, 5, 6. And those are numerical indexes or indices. If you do it the other way, which I'm used to more in like JavaScript, you do the name of the table and then the open braces and then an index with a string, which is a key. and then you add the value. So it's a key value system. So navigating that in general, when I'm normally doing JavaScript all the time, and also the 1 indexing versus the 0
that would
indexing.
mess me up.
Believe me, I've spent so much time on all of these problems because they all require tables. They all require like arrays at the very minimum, unless you make classes, which are also in Lua, which is something I also spend a lot of time is doing classes in Lua, which are essentially just super tables. That's where I think I spent most of my time was just trying to parse this into that data structure and then actually figuring out, whether a splitter was hit or not was almost beside the point. Not quite, but almost beside the point. So yeah, I think I quickly got it once I got that done. But what about you?
I don't remember what was hanging us up so bad other than, it was trying to figure out what was going on with the sample data. I think once we figured out that splitter didn't get hit, and then we were like, well, okay, this makes sense. Like looking at my code, like it's not complicated. It's literally a nested for loop. It's 2 for loops. I iterate over every single cell, going down row by row, and then if the one above me is either the S or a beam for its tachyon split, then I set my current one based on that. And if it's a beam or a dot above me, then I know what's going on. Or if my current one is a beam or a dot, then it stays that. It becomes a beam, and if it's a caret, it splits again. Was like it. And if it's not a beam or an S above me, I don't care. Is what that boiled down to. And I didn't do any memoization or anything clever with that. I literally just populated the grid and then went down row by column and got the answer.
Yes.
I found part one fairly straightforward once we weren't trying to do it live.
Yeah. It's amazing like how your brain works differently when you're performing versus when you're processing. I don't know. I'm looking at my code. Yeah, I did basically the same thing. I made a 2D grid and I went down the grid and did all the things you said. This also, another thing that I spent a lot of time on was building a grid class in Lua, which I kind of took from my Ruby class from before. But once again, I had to deal with the 1 indexing and the fact that it's a table, associative table, and not a normal JavaScript array. So it just took a long time to kind of suss that out. But in the end, I did end up with an awesome grid class. So now I have for future use, if I do it in Lua, I can just say like new Lua grid, and it has all the stuff that you would think. I went back and retrofitted like one of the earlier days where we had to count the neighbors. I think that was the one with the rolls of paper. Yeah, it's one of those things where whenever I start one of these years, because I still don't think about these problems in OOP like you do, I still do just kind of like I make up my data structures on the spot. Like I just do arrays basically. And it's always easier to handle once I make an actual grid or graph or whatever class and then do new grid, new graph.
It's not always the most efficient way of solving a problem, but for me, it's the most efficient way of thinking about a problem. Because once I have it isolated like that, then I'm like, okay, I'm operating at that. Like, what level am I going to be operating at? All right, I care about individual cells and their relative positions. Okay, that's my grid class, right? My grid class already knows how to count neighbors because I wrote that multiple times now over the last few years. I think I rewrote it in response to one of the problems this year because I was doing it very inefficiently. So, yeah. So let's talk about part 2.
Part 2. All right. So now that your analysis of the manifold is complete, as soon as I saw the word quantum tachyon manifold, I was like, oh man, like past trauma from previous years where I know there have been at least one, if not multiple problems where now they want you to be like, okay, you're shooting the tachyon beam from the S at the top middle like usual, but when it hits a splitter, it's not splitting left and right every time. Instead, it's splitting either left or right. And they want you to essentially count up all of the potential ways the beam could go. Like it'll go left this time, and then at the next splitter, it might go right or it might go left, et cetera, et cetera. So now you're counting up the number of timelines or dimensions that the beam could shoot through this field being split every which way. And I know, looking at my code, that I of course did it the brute force way, which was modeling that, and then every time it hit a splitter, choosing a random direction, and then counting that up over many, 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 many loops until you got an optimal, like to where it stopped changing the number of. Is that what it was? It reminded me of my Dectal algorithm.
Where you just try it a bunch of times and see.
Right,
and
where
see what's
I
best.
basically, I had the bot run that day's puzzle 10,000 times, and whatever its best attempt was becomes like the goal for, like the best way you could do it. It's not a smart algorithm. It's just enough runs that it evens out to like, well, that was basically the best it was ever going to do after 10,000 iterations. Yeah. So I basically did that and quickly realized that was not going to work because that would take too long. And then I found, right, this was the one where I found this amazing visualization where someone basically did the answer, but as a GIF of shooting the beam down and hitting the different splitters, but using an algorithm to figure out actually how many different timelines it could split at each time it hit a splitter.
Yeah.
And then for each column of the grid, and then once you get to the bottom, you've been keeping track of that the whole time, and then you just count those all up. So I definitely did not figure this out myself. I just saw the image, and I'm like, wow, that's really cool. And I figured out what they were doing based on the visualization. I coded that, and then that got the answer no problem. So I'm really interested to see how you actually figured this one out.
Yeah. So this immediately said dynamic programming to me, right?
Dynamic
the
programming,
thing where I'm like, and the way I always think about dynamic programming, and this failed me later in the admin of code, but is like proof by induction. If you remember that from math classes, where you'd start with, okay, this is this is how it works for this small number. And okay, now I can show that if I increment the number by 1, it looks like this. I'm like, okay, well, now that I have that, can I generalize the solution? If I know n minus 1, can I figure out n from that, right? Or if I know n, do I know n plus 1? Basically, what that boils down to for dynamic programming is start at the end for me, usually. So what I did is I wrote a little function called count paths to that took in my grid and my grid cell that I was looking at, and then I had a little memoization. So I was trying to figure out how to get to a particular cell in my grid based on these rules, right? So you go down the thing and you split. And then I used a little memoizer, which was just a little dictionary that was a map of, I think it was the cell that you're trying to get to and the number of ways you could get to it, right? Oh, it gave you that as the count. It was like the starting point and I guess I could just look at it. Oh, yeah, it was the location, and then that mapped to the number of ways to get there. And then I just recursed, basically. And so once it hit the end, so it's effectively a depth first search. And once it hit the end, I stored that value. So I'm like, okay, at the bottom one, if I'm looking at the bottom leftmost cell, by the time I've gotten there, I figured out how much it cost me to get there from wherever. And then I would go, and then so next time I needed that, right, if another one went to that bottom thing, I knew, oh, it's 1, right? There's only one way that this cell can appear. It has to come by this thing above me being a caret, or the thing to my upper right being a caret, or it has to come from the thing above me being a beam, right? Those are the only 2 ways you can get there. There's no caret either side, has to be a beam. So unless a beam comes in here, and basically I just counted and worked backwards. I think I actually described it better I started on the bottom row and worked my way up from any beam. So took the problem from the first part where it's like, what are all the little lines, and then just worked my way up from there.
So just to help me better understand this, if you're looking at the bottom leftmost splitter and you know the coordinates of that splitter, you write a method that figures out the cost to get to that splitter.
Basically,
is that
but it was specifically
what is the algorithm to figure that out?
It was actually how many paths can bring me to this. So every time
how do you figure that out?
Oh no, I lied. This one's even easier than what I was describing. This was it was kind of that, But basically, every time I got to a splitter, I just had to add my... Oh, because when it was a carrot, it didn't split below. It actually split next to, right? So if you had a beam that came
to the
into
side,
a carrot, it split immediately to the left and right of that. So I just looked at my east and west values at any point, and I knew, okay, if the thing above me is a beam, okay, that increments the number of ways I could possibly get to this spot right here, right? Because it was a beam, that means that there was a beam above me, which means it traveled south, got to me. That's one way. If there's a carrot to my east, well, that means there was one more way I could get there. Put that in. If it's a carrot to my west, that means there's another. Those are the 3 different ways that I could have gotten, and I increment on each of those, and then I just count that for the next for each of those locations, right? And so that trickles down, and then as I filter my way back up, instead of having to look at all the ones I've already calculated again, I stored off that information. So there's only so many ways any given cell can become a beam. Is basically what I'd figured out, and then I just kept track of those.
Huh. Okay, that's fascinating. I love that. I mean, that seems kind of like what the visualization I saw did.
Yeah, I just had trouble thinking about it the way they did. In particular, because they didn't draw the beams going all the way down, and it confused me.
Yeah.
I'm like, I need to see the path.
Yeah, I would have to say, like, I would rank this one fairly high in terms of just coolness of puzzle, mainly because it has a visual component. I always like when these puzzles have a visual component because there's something to look at and it feels like you're making progress when you see something appear. That's probably just the web developer in me. Like, just working in a command line the whole time can get a little uninspiring, but when there's something that's going to create like a visual that I can then see and I see that change as I make changes, that must be why I like that stuff more, even though I didn't
it's
really
great.
figure this out.
I like being able to visualize it because I can't see things in my head. So if I can actually see the picture, I can get it. And this one, like looking at the real input, it fits on my screen. Well, left to right anyway. It fits on my screen. So I could actually watch it go down. There's some later that there's zero way I could have visualized it.
Yeah. Although if you look at the subreddit, people are trying all the time to, like, there's people making visualizations of a lot of these problems, and it's like... It's like basically like game programmers just using this as like their data for their game and making,
Pretty much. There was at least one problem that I was like, this would work great with sprite collisions if I felt like dealing with that, but I don't.
Yeah, I mean, we've definitely.
But I bet I could use that library.
we've anytime there's like a 2D grid of any sort of thing, like moving like a path through a thing, it immediately makes me think of a game and game dev. So there's definitely a lot of overlap in these puzzles with that kind of thing. But yeah. Another cool thing about this one was that another thing that I do when I keep track of all this in my notes on the website that I'm keeping track of this, I have a little ASCII art image for every single one of them. And this one was a very easy one to make for because it was already there. There's an S and it looks like a little Christmas tree going down. So I was happy for that. All right, so that's day 7. Super fun. I definitely, without help, I would not have gotten this one, but, I'm okay with that.
That is okay.
So let's...
if the choice is don't get it or learn how to get it, why not learn how, right?
Yeah. Learning, I mean, this is as much an educational pursuit as it is any kind of quote-unquote competition. All right, so why don't you take day 8, Playground.
Day 8, Playground. So we are, basically what they give us is we have a series of, a large number of small electrical junction boxes. And they are trying to connect junction boxes together so that electricity can reach every junction box. And they have a list of all the junction boxes in 3D space. So a 3D visualization is immediately out for me in my head or drawing it because I don't like dealing with it. 2D, great. I can stick with my ASCII art. 3D, I'm like, no. Although I did strongly consider it for this one. So they give you all the junction box positions in 3D space. And then for part 1, basically they wanted us to connect pairs of junction boxes that are as close together as possible. So looking at all the junction boxes, which two are close together based on straight line distance? So standard Pythagorean theorem, a squared plus b squared plus c squared in this case, to get the distance. And then once they're connected, like once two things are connected, they're part of a circuit. And if you connect a third one into that circuit, okay, now you've got 3 items in a circuit and blah, blah, blah. And then what they wanted us to know was if you connect the first 1,000 closest pairs, then what was it? How many circuits are there, I think? Oh, no. The sizes, you multiply together the sizes of the 3 largest circuits. That's what it was.
Yeah. Mm-hmm.
Yeah.
Because the thing, it always has to be an integer, so it's easy to check. And so, yeah.
Right. Yeah.
Kind of a contrived thing to find, but yeah, that's what you had to do.
I think that's actually one of the cooler parts of the game development for this has got to be like, okay, well, what is the unique thing that we can make them return?
Well, it definitely means you can't have any questions that require like a really complicated equation as an answer or a short answer, like words. It always has to be something that's easy to check. So an integer is the simplest thing to do.
Solution for this one, for me, I spent most of my time making a new Node 3D and Graph 3D class in my little toolbox of things that I used here. And then I literally just populated that and then ran over all of the nodes and figured out the distance between every 2 nodes and then sorted that and went over the first 1,000 and added and connected the graph together. But my graph was smart enough to be able to keep track of the networks that got created. I call them networks instead of circuits, but whatever. Like what networks got created, and then when I was done adding them all, they had gotten populated as I connected items in the graph or nodes in the graph, and then I just reversed that list and multiplied the biggest 3. So very much just like straightforward, exactly what it told me to do.
Yeah, this was. For me, definitely following the instructions. This was the first time I made a class in Lua. This is the first time I messed around with that, and I made a box class to just hold the coordinates and hold the circuit ID that the box was on. I probably should have made an actual circuit class to show them being connected, because then I might have not fallen into that trap that you helped me with, which was that when I connected one box to another and that box was already in a circuit, I was not remembering to make the circuit it was already connected to a part of the same circuit it was being later connected to. So I was pulling the first box out of an existing circuit and switching it over and leaving the other one. And I kept, because I just spent a lot of time, once again, just parsing the input. I think that was a large part of this, was just parsing the input so that I could follow the instructions and see if the logic was correct. And I kept coming up with really close to the sample answer, but not quite. And then you clued me in on that. I was like, oh, of course. And once again, if I would have spent more time modeling it in a higher order structure than what I did, that might not have happened. But anyway, as soon as I did that, then I got the right amount and it was good. And then I just ran it with the input data and it was no problem. It was just that little snafu.
That's possibly one of the most frustrating parts of admin of code, is if you just don't quite put 2 and 2 together when you're reading the problem. Like, oh, of course. Like, as soon as I explained that to you, we're like, oh, yeah, of course. Right? But until then, you just weren't thinking about it that way. It's like, I'm connecting the 2 closest pairs. Duh.
Yeah, well, and I think that, once again, I spend a lot of time on these problems trying to just parse the string input into a working code model, and if you don't do it as well as you could, then you're spent doing more brain power in your head, trying to think about how this works and making assumptions about how it works. Whereas if you modeled it properly and carefully, then it would be apparent. That's why making like a visualization of this, like I said, if you made this into a game and you had a bunch of boxes and you could drag and drop one box to another, you would see the issue that I was coming up against, that I was not.
If you'd been graphing this,
circuits.
you would have been like, oh, it was blue. Why is it red now? Wait, what? Oh, those should have become purple or whatever, like depending on how you're visualizing it.
There's like a cognitive load that everybody has a different tolerance for, about how much time you're willing to spend to model it properly, or even knowing how to model it properly. And so I think I was probably just at a disadvantage because I was not modeling it as precisely as I could, and I was having to imagine too much stuff in my head and not seeing it. So that's another recurring issue I have with these kinds of problems, is that
I definitely fell victim to the sunk cost fallacy because of that in a couple of problems where I'm like, this is how I'm going to model it. And I'm like, okay, it's modeled this way. How do I, using this model that I've done, do this problem? And sometimes the answer was, that's the wrong model. But I was so like, well, this is the way I'm thinking about it. And sometimes I did that on purpose. Like in the earlier problems, there was a couple days where I was like, I thought about this. I figured out a better way. But I want to see how to do this problem this way because I know that's going to come up later.
You want to over-engineer the problem because you're already anticipating needing it later.
Yeah. In fact, looking at my notes for this, my solution to part 1 took around 10 seconds to find the data for the real input. And I was like, that's going to be whatever part 2 is, whatever's causing that to take 10 seconds is going to make part 2 impossible, whatever that is. So I think before I even looked at part 2, I went in and optimized parts of my like I already have all this stuff running through a profiler automatically. So I just pulled it up and was like, why? And a lot of times this year, what turned out to be what was slowing me down was actually printing things out. And not, but I had like a debug logger class. So I would turn off, like I would raise the level of input. So I'm like, well, it's not outputting. So it's not an IO thing. But the problem is that what would happen is it was still computing the string that had to be outputted and then just wasn't outputting it based on my log level.
I see.
So I was wasting so much time and I couldn't figure out why. I don't remember if this was one of the ones that did it, but in fact, I can just look. Yep, that was exactly what it was. This was the first one where I ran into that. So once I took out some of those debug statements, it went from 11 seconds to 3 just from taking them out. And then we got to part 2. Part 2 for this one is the elves don't have enough extension cables. So instead we need to put everything into one large circuit. And so then it's the same deal. Go through finding the shortest connections between two circuits and keep joining things until you have one junction. Until you have two junction boxes, and once you join them together, it becomes one. And then they wanted us to multiply the x coordinates of the last two junction boxes together to get their magic number. So I was glad that I had figured out my optimization. And just running it in my graph class that I'd already written and cleaned up, finished it. It said I wrote in about a minute.
A minute, okay.
So, and then I cleaned it up more to make it more efficient after that. But I had cleaned up the debug stuff, and then I just dumped this into my graph and kept running it until the length of my graph networks was 1. And kept track of the last 2 I'd connected, and then I spit it out. So this was solution 2 to this one was almost instant for me.
That's awesome.
Because of that.
I definitely don't have any optimization, but still, thankfully, the input data is not big enough, and it takes my system about 3.5 seconds to run part 1 and 2.
Yeah, yours is very fast.
Yes, and I mean, as far as my algorithm, let's see. Every time I made a new connection, I did a check to see if all circuit IDs were the same, and if so, I got the product of the 2 boxes x coordinates. And I wrote that this one was not nearly as bad. I spent a lot of time on the first part, just like I said, parsing and setting up a structure, and so this one was really just run it until you get a circuit. And thankfully, it didn't take long. So
it looks like I never optimized this one afterwards. So that's good to know.
If you don't do it while you're writing it, you're unlikely to do it later.
Sometimes I do. I don't think we ended up using this particular class again. I was expecting to use the 3D node class more times, and then when I didn't, I just never bothered to clean it up. But now I have one,
which is helpful because there will be more of these in the future. I assume so.
Exactly.
All right. Well, that was day 8. Day 9 is movie theater. And so I remember I finished 8-2 one evening and 9 had just come out, and I did part 9, and it was incredibly easy. Part 1 was incredibly easy because, well, let's look at it first. So you slide down the fire pole in the corner of the playground, and you land in the North Pole base movie theater. And so here, there's a big tile floor with an interesting pattern. And essentially, there are corner tiles that are red, and so they give you a bunch of coordinates of where those are. And once again, almost all the time was spent realizing that they're giving me the coordinates in X, Y pairs. So like 7-1 is go over 7 on the X axis and down 1 on the Y. Whereas most every grid I've made is the Y first. Like I go, like I make a table within a table. So the first table
because
is
you're
the
reading
row.
Y, and because you're reading the row and then you're reading the column. Yeah.
And then you're reading the X, but they're giving you the coordinates in X, Y. And so this was another day where I spent a lot of time on my grid class trying to, change that to work with the 1 index versus 0 index. I don't know. That the whole 1 index versus 0 index, my brain is thinking 1 index now. It's gotten to me. Like 0 seems weird to me now. That's what it did. I think of 1 being the first index. I know. And so if you don't want that to happen to you, don't use Lua.
Sold.
But yeah, so they give you these tiles that are red, and they want you to find the largest rectangle between 2 corners. So if you have like one red tile in 1-1 and another red tile in 3-3, you basically find the area of that space. And if that's the largest rectangle, then you've got your answer. And that's this one was really that's basically what I did. I just found the largest rectangle, and that was my answer. So
yeah, it was a very straightforward double for loop.
Yeah,
multiply everything together. I ran into a problem of learning a new thing in Python, which is that if in your class constructor you give a default value for a list of open bracket, end bracket, that becomes a global instance of a list because it's not creating a new one every time. It's always using that list that I wrote in the code. Like that creates a list. So instead I had to change it to the word list, like the method list, instantiating that. Then it worked. But I spent forever like, what is wrong with this thing? Why does it keep giving me this weird result? And it was specifically that. And it wasn't, I remember I was running this and like everything worked in the sample data. And then I'd run part 2 and I kept getting the same answer as the sample data. I was like, what is happening? Or I got extra information or something. And it wasn't until I started printing things out that I was like, oh. So again, visualization would help.
Is this an instance of passing by value versus reference?
Basically, yeah.
Right. And can you explain that just for, the listeners? Because that's a crucial thing to know in programming.
Yeah. So pass by value, if I have a variable called x, right, and I set it to 3, and I pass it into a method that uses pass by value, it's essentially just passing a copy of the number 3 over there. Yeah. But if I pass it by reference, I'm actually passing the actual variable x over there. So if you change
the memory
x,
address holding that.
Yeah. So if you change x, it changes it for real. So what's happening to me is I wasn't creating new entries in my list because I didn't feel like I needed to, because it was just I wanted it to start off as an empty list. But in my code, I created a list as the default option. Mm-hmm. And so it always used that. Effectively, what happened is the first time I called to create that class, it made this variable in memory for that list, that default list. And then every other time I made a new instance, when it went to go and I didn't pass in a list, it went and got that one that I'd referenced already. And then changing it to the actual method list, which quite frankly, those should do the same thing, but whatever. Then it was always making a new list every time.
This idea comes up a lot. It comes up in JavaScript. It comes up in Lua of this idea of of objects and whether you're passing the object that you made or you're passing a copy of it. And so I had to find a deep copy method in Lua. So because in the day 7 one with the beams, and you're trying to figure out the different timelines, I wanted to make sure that I was passing a fresh copy of the grid without anything modified yet to see where the beam was going.
Yeah.
And I wanted to do a deep copy so that it wouldn't like do it once, fill it with modifications, and then next timeline, it's using that same one. And I was noticing that in my sample visualization as it was doing the beam, and then on the second version through, it was doing the beam again, but it wasn't clearing any of the values. So it was using the same grid over and over again. Yeah. So that's something you have to be aware in programming in general, and it's the value versus reference. That's good. Okay, so part 2. So now we're going from not just having tiles that are red, but also having tiles that are green. So the corners are red tiles, and now they're connected orthogonally, up, down, left, right only, not diagonal, with green tiles. And now they want you to find the same thing, the largest rectangle, but it has to contain. It not only has to have the red tiles at the corner, but it also has to contain only green tiles. So you can't make something that's going to go outside of those green tile bounds into no man's land. I didn't even attempt this one because I saw it after working on 8 and 9 one night, and then I was like, this seems like this is going to be rough, and I just didn't even go to it. So this is all you. Since you solved it, how did you solve this one?
First off, I should say that my solution took an hour to finish. For part 1.
So not optimal.
No. So what did I actually end up doing here? Let me look.
I'm actually surprised that because anytime I've run something that takes more than 15 seconds, I'm like, nah, this is not going to work.
That's for part 2. Part 2
took
an hour.
But still, I wouldn't have even. I don't know if I would have waited that long.
Yeah. Well, I could see it was working. And I'm like, it'll finish eventually. And I went off and did something else, and I came back and it was done, and I plugged in the answer and it worked. So I was like, all right. I don't remember if I went and cleaned this up afterwards. Let's find out what I did. So what I did here, I spent a lot of time trying to get the fill function of my grid to work, right? So if I say, at this point, fill it with this color, getting that to work efficiently. And I did eventually look up a better fill algorithm than what I was using. And then if I remember correctly, I never ended up actually using I didn't end up needing the fill. But let's look through the code and find out. So I made a couple of new functions. One is value at, right? And that was essentially
whether it's green or not.
Yeah. And so what I did for that was I just checked to see if it was enclosed. If the point was enclosed, then it was green. I bound that's what I connected each of the red dots to, because it was like the next one in the list is the one you connect to, right? In a straight line. It wasn't like each is connected to all of them or something. So you got my red corner, and then I drew a line. I filled in all the ones to the next R with G, basically. And then I kicked that off, but I didn't fill because fill was taking forever. This was my first attempt at it anyway. And then I would just check to see, when I made a rectangle, if all the values inside of that rectangle were in fact inside the rectangle or not. Like, we're inside the weird shape that I was creating with the initial pattern. Where fill would have worked much better for that. Because if I just filled everything once, then it was a one-time cost and it would have been over. But couldn't solve that problem. And then I had to make a valid rectangle. I had a valid rectangle function that took in my grid and a given rectangle, which was just 2 cells. And then I had to look through that to try to figure out if, for a given rectangle that I had defined, because you did have to look at them all, I think. There's probably a smarter way to do that.
If it took an hour, probably not, but I don't know. Yeah.
Yeah. Then I would look at that and I would just run it through. Is it valid? And then afterwards, I cleaned up my fill function, and I think it worked a lot better. But basically, I kept a track of, I remember the biggest issue I had with this one. So I would do all that, and it would work. And I figured out there's a cheap way of figuring out if something is inside of a box, which is you just go from it to one wall. like you go from that to like infinity or to negative infinity or up or down, whatever way you want to go. You pick a direction, you go until you've left the grid basically, and you count the number of walls that you encounter. And if it's an odd number, you're inside, and if it's an even number, you're outside. Right? There's like that's something I ran into in past years. That's how you do am I inside calculations. But there's a caveat to that, which is if on your way out, you cross and you go through a wall that is heading in the same direction, right? So if you're going west on your grid to see where you are, and you go through a wall that is also going west, you're now counting all the points inside of that wall, and that messed it up real bad. And then I spent a lot of time figuring out how to solve that. I think I did go through Claude Code to solve that aspect of it because I was just tired of working on it.
Yeah,
but it was
definitely an endurance piece to these puzzles.
Yeah. So some of the span fill algorithms was where I ended up cheating a little bit, but I wasn't like, here is the problem, solve this problem for me. I was like, I got it down to this one little piece. I'm like, I don't know how to do this. Teach me how to do this. And then I learned that. So I have much better understanding of span fill algorithms now. But once I fixed that bug, it worked. And I optimized a lot of stuff in my grid class. I was trying to figure this out.
But like you said, it took a while to finish. It did finish. So there must be some like way to cut out a lot of the calculations to solve this in, less than a second, which is roughly how long all of these should take.
Yeah.
Or a few seconds. I think actually Eric says that no solution should take more than 15 seconds at most, even on an old computer or something. Yeah.
Yeah, and this one,
but you know what? Sometimes brute force just works, and you move on.
Yep. Sometimes it's like I get it, and I'm sure I could do. Again, if I had done a fill, I think it would have worked better. But also, like the number that ended up being the right answer for this one was some absurd amount of. Let's see. I have it written down. Oh, actually, no. It's just on here, isn't it? It was how many trillions? This is thousands. So it was 1.5 trillion was the area. So trying to count all of the boxes along the way wasn't doable. And so something about what I did was stuck in there. I think the right solution is probably to have computed all of the rectangles that were like definitely within the bounds. That were like without having to like cross paths or something, without worrying about the greens, and then like put them together in some logical way, some mathematical way. I didn't know what to do, so I didn't do that. I kind of brute forced my way through, but I got an answer, so therefore,
congrats.
It was good. Yeah, just so you know, I kicked off the solution to that one running while we were talking about how long it took, and it's still running. So I clearly never optimized it.
Yeah. Well, anytime like I get an answer for an Advent of Code puzzle that's like that it gets the answer, but it takes more than like a second, I tend to put in my code like a short circuit, and I just say short circuit this, the answer is this, but it would take too long to actually process it. Just, if I want to double check my work that I got the answer, this might be one of those days. All right, well, that was day 9. Why don't you tell us about day 10?
Day 10, the first one I did not get the part 2 to.
I didn't even get part 1, so.
This one's called Factory. I liked part 1 of this one. I thought it was interesting. We are given a machine diagrams, is what they called them. And it consisted of 3 parts, only 2 of which mattered for each part. The first part of the diagram is a little ASCII drawing of indicator lights. And it was, you want the indicator lights to match this diagram when you're done, right? And then the next section is a list of buttons. And when you push those buttons, effectively it's giving you a bitmap of what lights to turn on or to toggle, right? So
Toggle,
if I
right,
if I have a button and it's 1, 3, when I push that button, I toggle lights 1 and 3, counting from the left. And then the final section is joltage requirements. And they don't explain that in the first part, but you don't need it in the first part, so it's okay. In fact, they pretty much just say,
which means you will
ignore
need
that.
it in the second part.
Right. So what we had to do is figure out what were the fewest button presses required to correctly configure the indicator light for each machine, and then you sum those up. So since you didn't get it, I will talk about what I did.
I tried. I put a lot of effort into this, so I can talk about it, but I didn't get it. Yeah.
So, well, why don't you talk about the way that you tried to approach it?
Well, as usual, I tried to approach it in what is my favorite brute force method: lots of random choices, which I knew was not going to work. Like, I know intellectually that this is not the right way to do it, but I don't know how to do it, and so I'm hoping that the brute force will work. And this was the one that I spent a lot of time waiting for it to try things. But let me go back first. So essentially, I mapped everything into. I didn't make classes, probably should have, but I have a table that matches the indicator light diagram that you want it to be like, and then I have one that is all off, and then I start looping through all the buttons that allow you to toggle them, and I press random buttons until the base one looks like the desired one, and once it's done, then it moves on to the next one, and it does that a bunch of times.
When you say random button, do you mean you're actually just picking a random number and like what happens if this, or you're going through and like what happens if I push this one? No, I don't like that. What happens if I push this next one? No. Like, what do you mean when you say random there?
No, when I say random, I mean like look at all the buttons, choose a random one from the set, and push it.
Oh, that's an automatic indicator to me that whatever I'm doing isn't going to work.
No, I knew that was not the right way, but I had no idea what the right algorithm for something like this is. So I'm like, well, if this was literally in front of me, like a physical object, and I have to find out like, well, I mean, the thing is like finding like a solution is easy manually, but finding the optimal solution over a huge data set obviously doesn't work. Like you have to do it. It's going to take more time, and I know there's an algorithm. I don't know what that is. That's why we're having this podcast together, so that you can tell me what the right algorithm was. But that's what I did. I did random presses, and I did a bunch of that, much like the Dectal thing. And then I took whatever the optimal one was, and then I added it all together. The problem, of course, as you can tell, is that you have to do this that way many, many times. And 100,000 loops is not enough and takes like an hour and a half to do, which I did multiple times while doing other things, obviously. And in my notes, I started at 1,000 loops, which is funny because the input data actually goes pretty quick. So this is definitely a data set size issue, because I was able to get the right answer for the sample doing this. But as soon as you throw the input data, which is much larger, it falls down. I tried it at 1,000 loops, 10,000, 20, 40, 60, 100, and the optimal number kept going down, and I submitted several of them hoping that it just worked. But obviously, if you're doing it that way, you probably have to do it, I don't know, 1 trillion times to get the optimal solution. I don't know, but I never got there, and then I just had to move on to something else because I didn't know what to do.
The way you're doing that is roughly the same way that the AI technique called genetic algorithms work, which is effectively you have an answer, right? And then you mutate it. You create mutations of it. So let's say you were like, all right, I'm going to push buttons 1, 2, 3. That gives me this result. That's close, right? Cool. So now I'm going to mutate that. Maybe I add 1, 1, 2, 3 or something. And like you make several mutations and then you run it through it again and it says, yes, this is closer. I'm going to now use this as my seed. I'm going to mutate that one. But then there's a bunch of rules in there about like you don't want to, much like in real life evolution, you don't want to narrow the gene pool too much. So you still have some like outliers and stuff that'll like throw it way off. But like effectively that's what it's doing is it's winnowing its way towards an answer.
Yeah.
So I think that's kind of a cool approach.
No,
I did math.
Well, before you get into your solution, the one thing that I did change to it that was a small optimization was to not press the same button twice, because that's essentially doing nothing and is a waste of a calculation, because it just toggles the same things on and then back off, so it's like you did nothing. So that's
point,
one
actually.
that's one optimization you can add. And I think if I would have kept going with this and spent more time, I would have started to think about, okay, what are other combinations of buttons that don't make sense to press? Like it's a dumb algorithm, and it could get smarter, but it requires you to actually think about, okay, what is a smart button press to make when my indicator light is this and I want it to be that. But I don't know. I just never really spent the time thinking about that. I was hoping the brute force way would work. But anyway, tell me the right way.
I don't know if it's the right way, but it's what I did.
Tell me a working solution.
I viewed it as bitmaps. So
Sure.
my indicator light, if all the lights were off, was a 0. And if there was 4 lights and all 4 were on, it was a 15.
Lights.
Right? Thank you, Picard. Right. So I turned it into binary code. And then what I did is each button I also turned into a bit mask. So if I just had one button in my list, or if the button only changed one light,
One thing,
then I, like, let's say it was 3, then I would have 0, 0, 0, 1, right? Because that's button 3 changes just that one. And then what I did, but if I had like 1, 3, then I'd have 0, 1, 0, 1, right? So I was building it up like that.
Now I'm curious, what is the type of variable you're using to hold that information? A binary number?
Int.
You're okay, but so you're not actually saving 0103. You're saving the integer that equals.
Yes.
And then you're just when you actually go to toggle the things, you're flipping it back to an actual 0103.
So what I did for the
0101.
toggle is I used an XOR.
Okay.
Right. So I had my actual state of the indicator light, and I would just XOR. And when you push the button, I just ran an XOR against those two numbers, and that gives you the toggle effectively of those things. And that worked great. And then what did I actually end up doing for this? I have a lot of cruft in my code because I did not get part 2, and I have a lot of stuff in here trying to figure out part 2. But effectively, what I did is I just went through each machine, and I called this thing called goal path, which was basically I made it just iterated over the buttons, the paths of buttons you could push. Like pressing 1, 2, 3, the path is 1, 2, 3. Right. That was the thing I built. And so what I did is I started with a queue that just had the goal of like what the thing I was trying to achieve, the state I was trying to achieve. I put that into a queue called to visit, and then I had another one called visited, and that one was a list. Was a queue. Well, it was a list. Whatever. It was a queue of 2 numbers each. Right. So each item was 2 numbers, and then that was the button and the state, or the state and the button, whichever way it was. And I just started at the first one, and I'm like, okay, if I push, I started at the end state, and I'm like, what do I need? Or what would happen if I pushed a
Bottom
button
up.
at that state so that I can go backwards, right? I'm at this state. If I push button 1, what does that look like? Okay, that would change it to this. If I press button 2 instead, what would that look like? And I went through that whole list, and then I stored those in my queue of like, okay, to get from this state to this state, I can push this button, right? And then I just kept doing that until I got to 0, which was the start state of everything off. And using those 2 queues, I avoided going down the road again. So like I never had to worry about checking the same path twice. There's only a couple of ways I could get to this state. And it's if I press this button, or this button from these other states. And so then I just mapped state plus button equals thing I wanted, and I could go that way. And then I just worked my way backwards from that until I got to 0, and that gave me the path. And I did a breadth first search basically using that. And so the first time I hit 0, that was the smallest number of buttons to press. So this weird XOR int logic that I did, plus a breadth first search with some memoization so it didn't blow up in size was basically all it took. And that one went real fast relative to everything else. So that was part 1.
Awesome. Yeah, so go ahead and you can spoil part 2 because I'm curious.
Yeah, I did not get part 2.
Okay.
But what it wanted you to do was use that last section that I mentioned earlier, the joltages. So for part 2, you ignore the lights. So it's like part 1, turn on the computers, and you need to get the lights to be a certain part. Part 2, set the correct joltage with the fewest total presses. And so in order to get the voltage that you wanted, I tried this same approach, basically, of like, okay, instead of a 1-bit value representing each. So instead of lights, they're counters now. So the joltage requirements, like each one of those represents a counter on the machine.
Okay.
And so when I push a button, it increments all of the counters by 1. All of the counters that button represents by 1. So instead of turning on lights 1 and 3, it increments counters 1 and 3, right? And you're trying to get it till it matches the result. So I tried the exact same thing I did here, or did in part 1, working backwards from the desired state. But I probably overthought this now that I'm looking at it. I was trying to do the same deal with just XORing it. I was like, well, okay, Python handles unrealistically large numbers. Like, it doesn't care how many digits it is. I looked at my actual output and my actual input, and the largest count value I had for any counter was like 250 or something. I'm like, okay, so my biggest number I ever have to worry about in these counters is 3 digits, 3 base 10 digits. So I basically multiplied each counter by 1,000 to the power of the digit place that it's in, so that I basically made a base 1,000 number, and then was going to XOR that. It super didn't work, and it just blew up my memory right away. And I don't know. I never figured it out. Now that I'm looking at it again, I don't know why I wasn't just you push the button and then the numbers change. It couldn't have been that hard.
Yeah.
I think I was trying to find like effectively a hash of those numbers in that order.
Yeah.
And I just did it in a dumb way. So I imagine if I went back to this one, I could figure it out now that I'm saying it out loud. But it was hard. It was basically the same exact problem, but instead of on or off, it's
counters.
Fixed value, and there was no way to once you added something, you couldn't take it away. So I had like a is valid joltage method. So like if I did change it and any of the numbers were above the jolted state, it was like not valid. Don't go any further down that path. And I kept trying to like rip out stuff, but just never got there. Just never worked. When I run it right now, it just crashes when it gets to that. It like gets
your base 1,000 solution crashes. I'm shocked.
It gets to number 100110050100005, and then crashes. I don't even know what that number represents. I think that's the button. I think that's the final button. Was something like that.
Oh, I see. Okay.
Or the button map for the final machine. It didn't work. It was the important part.
I saw a lot. I saw a lot of scuttle, but on the subreddit about part 2 of this, talking about this Z3 thing algorithm. Do you know about this?
I didn't. I do now because people were talking about it for this.
Yeah, what is that?
And my fellow employees also use that. It is cheating, is what it is.
Okay,
as far as I'm concerned, it is effectively an equation solver. Like it's a library or a cloud service. I think the library calls the cloud service that is an equation solver. So you're like given all of these things. Yeah. Like here, given all these things, go figure this out, and then it like gives you the answer instantaneously, which is
like
great.
Wolfram Alpha.
And yeah, and I'm like, I should learn how to use this. That seems really useful, but also feels like I'm like, how's this different than me just asking Claude? Like, hey, I have this information, right? It's getting an answer, but is it you solving it? I don't know. And that's always the blurry line with Advent of Code. Like for me, I have a line in my head about if it gets to a thing where I don't understand how it did it, I don't want to use the answer for that. Like that to me is cheating. I don't really understand how Z3 works. I looked at it. SciPy is another alternative. Z3 exists in NumPy, and SciPy is like a wrapper to Num. And I'm like, man, I should probably learn what this is and how it works because it seems like it could be useful. But no. And this one seemed to be disregarding day 12 because I just don't have any input on that right now. But based on solutions, this seemed to be more difficult part 2 than day 11 part 2. And given that I also got an answer for day 11 part 2, granted with some cheating, I believe that.
Well, should we move on to day 11 then?
Let's do it.
All right. Day 11 is reactor. You hear some loud beeping coming from a hatch in the floor of the factory. So you go check it out. And now you're looking at server racks.
Hey, it's just like my college jobs.
Yeah. And of course, the elves are having problems with the server rack and connecting devices to each other. And I believe, so this one, so basically they give you a text file full of devices with names like AAA, and then a colon, and then some other devices with 3-letter names as well that are their outputs. So it's basically giving you kind of a map between devices and what's connected to what. And they want you to find the how many different paths lead from one device to another. So they give you a map of connections between devices, and they want you to find the connection, or how many different connections go from you, which is the device that they slap a label on, to the out, which is another device. Yeah. And I also spent quite a bit of time on this, but this was the first time that I tried to do breadth first search in Lua. Actually, in any programming language, because these kind of algorithms I'm aware of, but I don't really use them except in Advent of Code. So I decided, okay, this seems like something where you need to do a search through a graph and find like the best way to do it. And so I spent some time with I found a repo full of popular algorithms that had been coded up, and they had Lua version. So I pulled that in and I started studying it. And so this is a graph. This is like a graph class where you have nodes, which are your devices, and then you have edges, which are connections between devices. And then you should be able to give a properly coded search algorithm the start and the end, and then using the edges between nodes, it should be able to tell you, how many connections you have to go through to get there, and how many different ways you can get there. And so really the answer to part 1 was finding how many different ways you can go from one node to another node using those edges. So I spent a lot of time using this library, studying it, trying to understand it, and it worked on their test input, but it would not work when I gave it the input from this puzzle. And so I was I was stymied by that and couldn't go any further. So that's as far as I got on this. It's like I understand. I feel like I have a general understanding of what the model for this kind of puzzle is and how you're supposed to solve it, even if you do it manually, even if you just start at device A, follow it to an output, keep going until you get to the end, and like, okay, how many, that's one path. Okay, now what's a different path? What's a different path? I mean, it feels a lot like the last one with the button presses. It's like, I want to get from state A to state B. Yep. How many different ways can I get from state A to state B? And you can do that manually for a small data set, but when you get a large data set, you can't do that manually anymore because it becomes too big of a problem. So
the big problem there was that we weren't trying to find the most efficient path, unlike the last problem.
You were trying to find
a path. It
was
find
paths.
all of the paths.
Yeah.
And that turns out to be a much more difficult problem than just find the most efficient. So a breadth first search is great for finding the shortest path, right? Because you just start at one and you branch out until you hit the end. But then you'd have to keep going past the end of any of them to keep getting all the paths. Totally doable that way. I personally find coding up breadth first searches more annoying to do than depth first searches, which is why I don't generally like shortest path algorithms, because I have to do a breadth first search, but they're not that hard. Depth first search, on the other hand, is easier to code because I just do it recursively, and then that usually blows up. But in this case, a depth first search worked just fine. I made a little class called server rack, which effectively, I don't know why I didn't just reuse my graph class other than I didn't have coordinates for anything. And my graph class very specifically was expecting spatial coordinates for things.
Yeah.
I just need to make a generic graph class, I guess. And then I just did a depth first search, right? So I started at the start key, which was U, and I tried to get to out. And I, starting at that first one, every place I could go, I ran a recursive depth first search from that new node to out until I got there. I didn't memorize anything. I didn't do anything weird, and that just worked. That one worked very, very well. I got the answer pretty quickly. Yeah.
Yeah, I feel like if I went back to this and, I probably don't even need a library to do this now that I've looked at the library that I found and I kind of see what it's doing, the whole idea of nodes and edges and that kind of thing. I could probably just code that myself, I think. But this still just shows, this definitely shows my weakness in these kinds of algorithms, that I just don't do these algorithms, so they don't come to me naturally at all. And I'm not sure how you would do this with a large data set without doing that. I don't know what the other way to solve this. I don't even know what the brute force method is. I guess
you know what the brute force message is. It's basically what you just described, right? It's you go through starting at the beginning and you look at every single path.
Right. And because
it would just take a while to compute all those.
Yeah, I was writing down basically what you said. You start at A and you work your way to B, and you make note of that path, and then you do it again. But when you get to a certain node, don't go one way, go a different way, and you keep doing that until you have only unique paths.
It's actually go both ways, because I'm like, okay, I'm at a point I can go either BBB or DDD. Which way do I go? Well, tell me how long it takes if I go BBB, and tell me how long it takes if I go DDD, and then I add those together, and that's how long it takes to get from my node to the end. Right? Is how many unique paths are there this way? The way I did it was probably the most brute force way, which is just the recursive depth first search. Is probably the most all right, if I was doing this by hand, this is what it would look like. But did not work for part 2.
Yeah, so what is part 2?
Part 2, instead of starting at U and going to out, you're starting at server, SVR, and trying to get to out. And it turns out there's a whole lot more paths from server to out than U to out. So for U to out, in my input, there was 523 paths. The answer I got, there's more than that for part 2 also. It's not just server to out. It's server to out that also contains 2 specific points along the way, DAC and FFT in whatever order. So this is actually not all of the paths from server to out. It's all the ones that include those, which you would think would make it harder.
That just a simple... I would think if you're finding all the paths and then you just filter it out for the ones that have those nodes in it, is that not the way to do it?
That's what I thought. Hold on, I'm
big
counting.
Data set kills that.
What is that? Hundreds, thousands.
Let me look at my input.
Hundreds, thousands, millions, billions. It is 517 trillion was my answer.
Yeah.
That's how many paths. So doing it the other way, where I was keeping track of the actual paths as I went, was not the answer to this problem. And was the thing. This is the one I ended up cheating and using Claude Code to optimize that. Because I'm like, what am I doing wrong? And the thing I was doing wrong was trying to actually keep track of the paths as I went. Because I wanted to know what I'd visited, so I didn't revisit nodes if there was a loop.
Yeah.
First off, there were no loops. So that worry of mine could have just gone away.
Okay.
And I should have just checked for that right away. But I didn't. So that was my bad. And then the other thing is that then meant I didn't need to keep track of the paths. I just needed to keep track of had I visited those 2 nodes along the way. Or which of those 2 had I visited. So that ultimately is the algorithm that it spit out for me from Claude Code was counting the paths. Not give me all the paths, but count the paths that include these 2 things between these 2 points. And then it's basically the same thing I did in the first part, just much faster. Like I went from this is never going to finish, and then I would die from out of memory, and like my system would get all messed up and it would like lock it up while I was trying to do it. Like anything I did to try to optimize it with that full path wasn't doable because there's 517 trillion of them. My computer just literally couldn't keep. It was such a big jump between you to out to server to out that like my brain couldn't comprehend it. So when I got this gigantic number, I'm like, well, that's clearly wrong. And I plugged it in and it was like, no, that's right. And I went, what? So that's how I accidentally cheated because I hadn't fully grokked what I was doing at that point yet.
Yeah.
Like what the optimization had done was before I plugged that in. Otherwise, I'm fine with it because everything else I did was right. It was just the optimization bit around that I wasn't wrapping my head around. And if it had said, count the paths, count the number of paths, don't worry about like getting all of the paths, I would have been fine.
It's funny. Like if we weren't running these solutions on, non-supercomputers, but we were running it on a supercomputer, like a farm, and it could do these kinds of brute force things like, instantaneously, like you would never learn about this need for optimization because everything you could do the least inefficient algorithm ever like mine and it would work.
Well, that's the whole danger of quantum computing, right? It's effectively what they do, like in a quantum computer, it goes in, it just solves all of the paths at once.
Yeah, but parallelly, right?
Yeah, like massive parallelization.
Exactly.
Like the reason we don't have quantum computing is because we can't actually do that. But you can simulate it real fast if you have a lot of containers or something.
Exactly.
Like it would not be that hard. If you don't care about resources, you could solve any of these problems pretty quick.
Which I think is a great segue to the final day, day 12.
Yeah. All right. So day 12, I only saw part 1 to this, and I hate these kind of problems, so I didn't try it. But let me kind of talk about what it was, and then you can talk about how you solved it after I say what I was thinking of for how to solve it. So day 12 is Christmas Tree Farm, which just puts the Taylor Swift song Christmas Tree Farm stuck in my head constantly.
Same.
Since I read this, that is the only song that is played in my head. It's been on a loop. It's really irritating. In fact, I had just gotten it out, and then I read the name of the problem again, and now it's back. But basically, what we're trying to do is place presents under trees in specific boxes. So they give you the shapes of packages
in a 3x3 grid.
So and are they always 3x3?
They're always 3x3, even in the input. Yeah.
Yeah, I couldn't remember. That was one of the things that makes this problem much easier.
Oh my gosh.
When I initially looked at this, I'm like, oh, these are going to be huge presents. And then you have to fit them into specific size grids, a certain number of each. So like in the sample, the first one is a 4x4 grid where you have to fit 2 of the number 4 shape present, which just looks like a C, into the grid. And then the question is, can you? Right. And so for each of these grids and their little map, of number of presents. Can you do it? Is the question. But it's not like you can keep the shape, but you can flip and you can rotate the shapes. Which, again, knowing that it's only 3x3, not as bad as I was worried it was going to be. I could probably do this. But then, so for each region, what do they call those things?
They are regions, yeah. The size of the region.
How many
and the
of
number
the regions can fit
needed.
the presents listed? Yeah.
Yeah.
And then you just say and then you just return that number. How many regions can fit all of their listed presents? There's some obvious brute force ways to do this, which would be literally calculate all of the rotations and flips for a given present, and then find all of the places that it could physically fit in a grid. Yes. And then kind of tree your way out from that. Like, all right, I put one, there's 6 different ways I could put shape number 4 in a 4x4 grid or something like that. What does that actually? Can I fit another one? Yes. And as soon as you find one where the answer is yes, you're done. You're like, I don't have to look anymore. But if there's 3 presents, you do have to look at like every combination of 2 shapes that you could do that would fit that, and then you have to check the third one can fit into any of those or at least one of those. My thought on how I want to approach this is similar to that one where I did the bitmap with the indicator lights. Was just turn the presents and the grids into bitmaps, and then I could probably use some XORs to very quickly like just go through that and see. So all the things I just described about previous rotations or calculating all the valid rotations and flips, basically just go through those and then try them all. But it would be more efficient because I'm not having to deal with 3D shapes. I'm dealing with numbers, 9-digit numbers instead.
Yeah, thankfully this is not in 3D space because they have gone there before, for sure, and they didn't go there this year, thankfully.
And I can't even visualize that. But this, I'm like, okay, I get that. That's fine. So how did you solve it?
Yes. So first of all, this is, do you want me to actually ruin this puzzle for you or not?
Yeah, I have ideas about how to solve it. I'm curious how you went about doing it.
Okay.
I'm confident I could solve part 1.
Yes.
Once I spend some time on it.
So in terms of Advent of Code and this puzzle and getting the solution, it's a troll. And it's a troll because if you actually do, I think, all the things that you're talking about, finding out all the different, potential rotations, et cetera, and then you look at the, let's see, how big is the input file? It's still only 5 presents. They're still 3x3s. The space that you have to fit them and the number of presents you need to fit to them goes up way, way higher, and you're up to like over 1,000 regions. So, definitely a big number kind of issue. You don't actually have to do any of the rotational stuff at all. The problem, or the troll, is that, and I didn't figure this out, but I went on the subreddit because I'm like, I have no idea how to do this. And they're like, this works if you just put the presents right next to each other. If you assume they are all 3x3 squares and you just see if I put them right next to each other in a line, do they fit in the area given? Then it works.
What? That's cheating.
Yeah. No. Well, I asked you if you wanted me to ruin it for you, and you said okay, so I went ahead and ruined it for you.
I'm fine with that because that's not the way I'm going to solve it.
Good. But that's how you get the answer. That's how I got the answer.
Literally, if it fits, it fits.
If it fits, it fits.
Like you don't it's a cat problem. You don't have to rotate them. You don't have to flip them. Nothing.
You don't have to do anything. Nope. Because and I think it's not so much that you don't have to. Like you could do that, but it just works out that what they give you, it doesn't matter. That's why it's a troll. And it's the end of the year, and I think it was definitely a gimme. Like so really the answer to this is realizing that you don't have to do any of that, and you get the same answer if you just put 3x3 squares next to each other. Which like I said,
can
it's
just
kind
multiply each number by 3 and see is that and
too is
wide?
It less than the area of the yep, and you still get the answer. Now, what's crazy about this and what I don't understand is that
That shouldn't work.
Right. It shouldn't work because it kind of invalidates the whole problem. And that's why I called it a troll.
Yeah.
It's a troll problem. Now, how you feel about that or not at the end of the advent of code, I don't know. But no, what's weird is that I can't get the sample data to give me the right answer.
Well, because I don't think it would with that algorithm. Because
No,
it actually
it doesn't.
does require, because it has a 4x4 grid that you can fit 2 in that wouldn't fit 2 3x3s. Like immediately, the very first part of that doesn't fit under that.
Yeah, the sample data is supposed to be 2 of them work, but the first 2 work, but the last one doesn't with that algorithm. And I was like, well, that's the first time that's ever happened in Advent of Code, that I got the solution, but not the sample using that algorithm. Now, I'm really curious to see you do it the right way and see, and I'm assuming you'll get both of them, but now that you know that, I don't know how you feel.
Well, what I might do is use that to check my work instead.
Yeah.
Because what'll be nice is if I can just run that cheap one off on the side, I can see where I'm getting the problems wrong and visualize that one, right?
Yeah.
Because I mean, the biggest problem I have in here is like 50 by 50. I'm looking for a bigger one as I scroll. Oh, there's a 52. Ooh. Well, like the grids don't get that big, so it's totally possible to dump out a visualization for this guy.
Yeah. You could do that, and I mean, I think it's still worth doing that, but yeah, it's I mean, it's kind of funny, but also not. I don't know. It's one of those things where, like, at the end of an Advent of Code, like, I'm okay with a gimme. I'm okay with realizing that it's not as hard as it looks to get the solution, but it is kind of weird. It's not something they do often, I think. So it's a little uncommon for them to throw one. But I think the idea was like to overwhelm you with something, because I think if I read several people saying that, like, if you actually run this on a big enough data set, it kind of becomes like an NP problem that it's actually like it may not be solvable at a large enough data set or something. So to make it where, like, yeah, but if you just discount all the things we just said that you have to account for, you get the solution anyway. That's 6, 7.
Well, and there's no, but there's no way that would work for part 2. Like whatever part 2 is, I'm sure that is not the case.
Right. Well, I mean, do you want me to ruin part 2 for you?
Yeah.
Since
there
is no part 2. It's all the stars.
Oh, it's one of those again?
Yeah.
So it's a gimme, it's a gimme, and then another gimme. So if I just solve day 10 part 2 and day 12 part 1, I get the entire thing then.
You get the entire thing, yep.
Oh, well, no wonder everyone had gold stars for day 12.
Yeah, exactly.
You're the only person I saw that had a gray star or silver star for day 12 because you don't have all the days. But everyone else gives you the whole, everyone else at work.
It gives you the princesses in another castle kind of answer until you get the rest of them. Yeah. I mean, like, well, since there is no part 2, like, what do you think an actual part 2 of this solution or this puzzle might be? Like, what's the harder version of this?
Oh, what's the smallest grid size you can fit all of those packages in?
What's the most optimal space-saving maneuver you can make?
Right.
Now,
and then you multiply those grids together, and then that's probably NP.
Well, or not only that, but also grids, present grids of different shapes, like non 3x3s, like a 3x4 weird shape or something.
Or like the first one is always fixed in this. No, because that actually makes it simpler, right? Yeah. It'd have to be something like the grid sizes are different. Oh, actually, you have all of those grids are next to each other in this pattern, and you have all of the presents that it listed out. Can you fit all of those presents into all of those grids? Like something like that is a part 2 that I would expect. But the part 2 on day 25 is always.
It is.
Do you have all the stars?
It's the same for this year. Yeah.
Yeah.
Right, you could also do there can be partial overlap, because like in real life, sometimes you put presents on top of each other.
All the time. I don't want presents spilling out into the rest of my living room.
Yeah, you
Although
don't.
This
You
year
don't.
we have
You,
no presents under our tree. So
yeah, you don't put presents in a perfect, flush with each other way. They just kind of throw them all in a pile. Yeah,
it wouldn't look good if you just put them all like in a grid. Even
Right,
I don't like that.
It would look strange. It would look inhuman, perhaps.
Also, I rarely have C-shaped presents. I don't think that's a normal.
That
Like
is
the
a-
shapes of these presents are weird. I thought it was going to spell something. So if you look at the shapes of like in my actual input, if I look at the shapes, like the first one doesn't look like something, but then the second one looks like an I, like a capital I, and then the second one could be a lowercase a, or it could be a 9, and the next one doesn't really look like anything, but then there's an F and then a U, and I was like, okay, maybe some of those presents are supposed to be letters, and if I put them next to each other, it spells something interesting, and that's good. But I never had a chance to look at it.
Oh, part 2 could have been like, how you have to arrange the presents so that they spell out something at the end, and what's the optimal way to arrange them so they spell that out, or the fewest number of presents used, or something like that. I don't know.
Right, like the 2, the one that
Like
looked
your
that I said
Christmas
could be
tree
an A
problem
or
that you
9,
love.
that could be a Q. Yeah, I hate that. At least this one would be, I could compare it against something real.
Yeah.
It looks like a Christmas tree isn't an answer. A Christmas tree looks a variety of ways.
Exactly. Yeah. So the ending of this one was, it was interesting, but I'm sure lots of people did lots of cool algorithms and things. But I'm like, oh, you can solve it that way. Okay, done. Because once again, I have a note in here about OMG, the amount of time I've spent just dealing with files and tables and classes and looping the correct things just to get the sample to load and process properly. So much time this year just spent, because the way that like files are handled and turning that into an input text or string and making a class and making tables and looping all those kinds of things that I've probably solved already in Ruby and JavaScript, I had to like kind of reinvent a little bit in Lua. And you'd think that like maybe I shouldn't do it in Lua anymore because maybe it's not the best way to do this, but I think it's just more that I just don't know. I just didn't know. So I had to spend a lot of time doing minutia like that, which is not really like solving a problem. It's more just like, how do I get a file into Lua and look at it and make stuff, make internal models out of it. I just spent an inordinate amount of time doing that. So, but also
on the other hand, you learned Lua better. So
right. It was definitely worth it to learn Lua better, but I remember you saying at the beginning that like you didn't want to necessarily do Advent of Code in a language you weren't as comfortable with, because there is a non-trivial cognitive load spent on learning that language to do the things you already know how to do in other languages that not only just takes time, but also wears you down endurance-wise to where by the time you finally just get a working model, you can actually start working out the logic of the problem, and you're like, oh, it's 2 a.m., I'm exhausted, I want to go to bed. Was that a good idea? I don't know. So.
Yeah, and I think that's one of the things that really gets to me on this in Advent of Code is it's like an addiction or a compulsion to try to get the answers. Yeah. Once I've read it, like I made a very conscious choice this year not to do the problems the night before. Right? Like when they come out at 9 p.m. my time, I'm like, I'm not going to do them then. I will read them and let it background think in my brain. And sometimes when I woke up, it was like a no-brainer to solve the problem, especially in the first few days. I like didn't even have to think about them.
Yeah.
But I definitely ran into my share of frustration with these this year. But there was only 12 days. So like the frustration didn't last, because usually like the last week of Advent of Code, I don't enjoy. And then it's on my birthday, and that's not nice.
Yeah. And
give me a problem I can do on my birthday.
Just the general busyness of the holidays and events and getting presents and still having to work and et cetera, and then also throwing on the cognitive load of Advent of Code throughout that entire time is, a real burden. I mean, that we're, voluntarily doing, but still it's as much fun as it is a burden sometimes. And so, it being done and us kind of wrapping it up and then still having half the month to go, I think this is the way. And I'm sure Eric is feeling the same way after 10 years. He's like, I don't want to do this anymore. And so this is his compromise. And yeah, I'm cool with this. It's good. Yeah. It was fun.
Good job,
as
Eric.
it always is. So,
indeed.
All right. Well, we got through all of Advent of Code 2025. We did not have Richard on this year. I believe he is out doing something and hasn't even, like I said, hasn't even finished the whole thing. So,
or he's finished them all and he just hasn't uploaded them. Like,
yeah,
he might
he
just
doesn't have
have
internet
everything sitting
he
on
is,
his computer or something.
That's true.
He's going to come back and immediately just like all the stars.
Yeah, I'm sure he can do all these. None of these seem no individual problem this year felt any harder than any individual problem from last year. So,
I agree with that. Yeah,
yeah.
Generally speaking, it felt easier because there was fewer days of impossible problems.
Yeah, and you're right. Like, yeah, after the midway point of a normal year, like it doesn't matter how hard the problems are. It's just like my brain is it's not running at 100% by day 14, 15, 16. So
absolutely not.
I'm already at a disadvantage. So yeah, I think it's good to get in and out and be done. So, well, thank you, Eric Wastel, for yet another fun holiday programming challenge. It was fun.
Yeah.
And I spent a lot of time learning Lua and building up libraries and being frustrated and figuring things out. And you strolled through Python yet again. And maybe I should just go back to Ruby next year. I think I might.
It's just a question of like, how much do I need to get out of this and how much time do I have? And this year, I was like, I'm not going to have time for that.
Yeah.
I'm going to do what I can do in the time that I have.
Yeah. I'm curious to talk to my coworkers on Monday about where they are, since, like I said, it seems like they all dropped off at problem 9. But I'm curious to get their thoughts just on what they thought about it, since they'd never done it before, and we've done it.
That does seem to be when most people dropped off, was around that time.
Yeah, around the 75% mark,
which is pretty typical of the normal one. Actually, is around that amount of time.
Yeah, I think we found kind of the statistical top of the bell curve of where people are like, yep, we're in, and now we're starting to drop. So,
but on the other hand, I only have 2 problems I have to solve now that I've hit the end of the year, instead of like 10. Because usually I get to the point of I haven't been able to do them a bunch, and then I get to the end, I'm like, well, I'm never going to go do those. I have 2 problems. I might actually go do those once I'm not working. Like I'm working this week, and then after that, I'm on vacation through the rest of the year. So I might play around with this again, or I might write some games. I don't know. Let's find out.
I mean, I'm assuming that once the next time we meet, we're gonna regroup on game dev, because we took this little side route into Advent of Code as we needed to. It was a good break from thinking about game dev. I was actually getting a little not like fed up or tired, but just like it was a lot of thinking about just game dev and not anything else.
Yeah, we needed a break.
Yeah, and now I need a break from Advent of Code, so time to go back.
Yeah. Maybe we still need to throw an occasional like, hey, I found this interesting article episode in to break up the game dev here and there.
Probably not a bad idea. Yeah, variety is good.
I hear it's the spice of life.
Yeah. Hopefully everybody out there also was able to do Advent of Code. It's super fun. There's 10 years before this to do. I went back and I might do some, like, whenever we do Advent of Code, it puts me in that Advent of Code mind. And so I start looking at like older years that I haven't done yet. And especially since I started one in Lua and now I've got Lua on the brain, like I can probably handle that year a little bit better than when I initially did it. So I might go back to that, or I might just stop doing it until next year. Who knows? Yeah. But thank you for listening to this episode of Hacking the Grepson. You can listen to more of our past episodes at hackingthegrepson.com. As we've said before, we have several years of Advent of Code discussion on there and lots of other stuff. And until we next talk at you, we now return you to your regularly scheduled lives already in progress.